So I'll speak about our joint work with Gal Beniamini about Wilkie conjecture for restricted elementary functions. So what we are doing, we count rational points on some analytic sets. So so the first thing so what does it mean we count rational points? So usually there are infinitely many rational points on the set. So in fact, we count the asymptotics, how fast their number grows when the denominator grows. So we should define height. So for reduced fraction, PQ rational number, we define its height as maximum of numerator and denominator. For a vector, we define the height of the vector to be the maximum height of its coordinates. And for a subset in Rn, we define the A of Q to be the set of rational points, and A of QH is the set of rational points of height at most h. So this set is definitely finite. And so what we do, we try to understand asymptotics of the number of such points in the set A as h goes to infinity. So this is the general question. Sometimes it stops, stabilizes, but not always. So the subject started a long time ago, but the kind of important advancement was the theorem of Bombieri-Pila in '89 and also Pila in '91. So what we do, we take an analytic mapping of an interval to the plane. And what we get is analytic curve. So we call it gamma. Suppose the theorem says that gamma doesn't belong to any algebraic curve in R2. Then the number of rational points on the curve grows very slowly. It is very small. So it grows slower than any degree of h. So to understand what happens, so it is kind of useful to consider several examples. So so on the diagonal, if f1 and f2 are just equal, then this is certainly algebraic curve, and here the number of this number is of h squared, more or less. So just all rational points on the interval. If you take a parabola, let's say, then what you get is O of h. And in general, the curve of degree d, you expect O of h 1 over d. And analytic curve is kind of algebraic curve of infinite degree. 2 over d, sorry. 2 over d, yeah. And kind of as d goes to infinity, you get estimate of this type. And so this is the intuition behind the number. Now so as I formulated it, this is for a graph of for a curve, gamma is parameterized by an interval, but actually you can take any curve, irreducible analytic curve gamma, and parameterize it by finitely many intervals. So it's kind of true for any irreducible curve, irrespective of the parameterization. And the conclusion fails if gamma is algebraic, as we see there. And there are examples which show, if you carefully construct analytic curve, it shows that you cannot get any better in general without imposing any restrictions on the curve. So this is the starting point of the business. Now the outline is so how it is proved, and so what I want to.
When you say analytic, you say analytic non-algebraic.
Analytic non-algebraic, yeah. Now, what I intend to do is the proof is really kind of calculus of the first year proof. And so I want to give the idea of the proof. And so the general general ideology is the following. We show that all points on this curve of height h belong to about h of epsilon algebraic curves of fixed degree d. And this is the main fact, a main kind of point in the proof. Okay. So what I do now, I want to show that I have several points on the curve, points of height h, and I want to prove that they belong to an algebraic curve of degree d. How I do it? So how we show? So we have several points on the plane. How we show that they belong to the same curve of degree d? The simplest way is the following. You look on the values of, you take monomials up to degree d. There are mu of them, and compute their values at all these points. If the values are linearly dependent, then there is a linear combination of these monomials. It means the polynomial of degree d, which vanishes at all of them. So, in other words, the points lie on the same curve of degree d if this so-called interpolation determinant vanishes. And this is the main player of the business. So, so our goal, again, we take several points here, and we show that the determinant vanishes. Okay. So, so what we do? So the first, we take the points which lie very close one to another on the interval of length delta. Okay, and then it is clear that the determinant should be very small, because when they all coincide, we certainly get 0. So if they are very close, we'll get something very close. And moreover, we can more or less explicitly compute the upper bound for this interpolation determinant. So again, we have this curve as before. We take points which are parameterized by points on the curve, points pi, which are parameterized by values of parameters on the small interval, and get this state. Okay, and what is the proof? You approximate these monomials. So we should evaluate these monomials at these points. So in other words, we have these functions, which are just smooth functions on the interval 0, 1. We approximate them by Taylor polynomials of degree t with some remainder, and substitute here. The idea is that if these Taylor polynomials are just degrees, then all these, the rows of this matrix will be of order delta in this degree. So altogether, the determinant of the whole matrix will have this order. And if you have polynomials, general polynomials, this is more or less the same, because you get linear combination. Clear? Okay. So you compute, and you get this bound, which is exactly, because mu is of order d square, you get exactly this bound. So in some sense, what is used here is that the curve is one-dimensional, so that the Hilbert polynomial just has degree 1. So this is upper bound, and then there is a lower bound on this interval, on this interpolation determinant, which just follows from, it doesn't need anything. You have just square matrix, and you know that, no, almost. So you have square matrix, and you know the entries of this matrix are rational numbers, and you know their denominators. Their denominators are at most, okay, almost h, slightly, okay. So h to the power d at most. And so you just compute the denominator, and then you get that your determinant is a rational number with a denominator at most something. And then this is the main idea of the kind of the theory, that if you have a rational number with denominator at most this, then it is either 0 or at least this number. Yeah. So if you have a rational number of m over n, it is okay. It is either it is bigger than 1 over n, or this is kind of the whole idea. So we have these two things, and we compare them together, and what we see is that if delta is sufficiently small, then this upper bound becomes bigger than this lower bound. And this is possible only in the case when this interpolation determinant vanishes. This means that if you take points, rational points of degree of height h, okay, which are parameterized by ti, which are close one to another, sufficiently close, then they all lie on some polynomial on algebraic curve of degree d. So if we have this curve, if this, okay, this interval is short enough, then all of them in fact lie on the curve, algebraic curve of degree d. Okay, so now the kind of the Gabrielov theorem says the following: if you have an analytic curve and you count the number of intersections of this analytic curve with algebraic curve of degree d, then there is a uniform bound on the number of intersections if, okay, the curve is non-algebraic. So it can coincide with the curve of degree d, but if it is not an algebraic curve, then intersections are just points, and there is a uniform bound on their number. And this is the statement in the same spirit as the fact that analytic function has finitely many zeros on the compact set. So it is finite, but it is completely unconstructed in general. Okay. So taking together, we see that if you split this interval into intervals of this length, then on each interval of this length, points we are interested in lie in the intersection of our curve with polynomial degree d. And so the total number is number of intervals, the h, okay, times m of d, the Gabrielov's number, which is exactly this number if you take d bigger than 1 over epsilon. So we just split to the small intervals. On each interval we have fixed number, at most fixed number of points. And the number of intervals is exactly this asymptotics we need. So the arguments are very simple, but somehow they surprisingly work together. Okay, so so this was the starting point. Now certainly you want to generalize it to higher dimensions. So what happens? Okay, so if you so what happens with higher dimensions? So you now first thing is that it could happen that the surface in R3, for example, is transcendental, but inside you have an algebraic curve, and for algebraic curve you have these asymptotics. So as soon as you have algebraic curve, this whole bound fails. So you have to throw this away. So the only thing where you can count is outside of this algebraic set. So we, define algebraic set part of the set A to be the union of all positive dimensional connected semi-algebraic sets contained in A. So we just take all pieces of algebraic curves or surfaces and lump them together. We get algebraic part of the set, and we don't know what happens there with the rational points because of this phenomenon there. Okay. So let's take the complement. It is called A transcendental part. And this is where we can count the rational points. So this is an example how this thing could look like. So this is kind of the curves can be dense in the algebraic. Take x equal. So for example, in this example, so for any rational number, you get algebraic curve inside your set, and should take all of them away. Then we cannot. Second, we worked with analytic curves. So in general, there is no hope to prove something for all sets. So you have to take your set from some tame category. So from you should be able to work with this set. So it turns out that the general framework is all minimal structures. So this is class structures which are generalizing semi-algebraic set, which we'll meet two examples in a way. So typical example of O minimal set is kind of subset of unit cube. The whole theory is real. Unit cube defined by algebraic equalities and inequalities. Analytic. I said algebraic. Analytic. So and then in this, so we take O minimal set A, and then for every epsilon there exists some constant such that the number of rational points of height h in the transcendental part of your set is at most c times h to the epsilon. So it is generalization. You assume the natural assumptions, and you get the result. So Gal, you will speak about it, or I will speak about it? So the question is why it is all this is interesting. So here's an example how it is used in kind of how it can be used to prove finiteness of the number of rational points. So suppose we take a torus, two-dimensional torus, and we want to count the torsion points on a curve inside this torus. So there is a we want to prove that this is their number is finite. So there is a trivial example when this this p is something like x to the m equal y to the n. So this is subgroup of C2. Then certainly it has infinitely many torsion points. Turns out that if it is not a translate of a subgroup, then it should contain only finitely many torsion points. So this is there are many conjectures of this type. So how you prove this thing? So you look on the okay, you want to count the torsion point, so you parameterize the torus, okay, the real torus inside C star square by exponential map, yeah? So we have here C star square, and okay. And here we have just the usual square, which is goes by pi here. And it covers the, okay, the torsion points lie on the, okay. In the side, this real torus. So this square just covers this torus, and under this covering, your torsion points become, the preimage of torsion points are just rational points. Okay, okay, here we had some curve V. So here we have some, its preimage, I don't know, A. And so we want to count the number of rational points on this set A. Okay, so the V is algebraic, but pi, V is here algebraic, but pi is exponential. So A is not algebraic except if it is a subgroup. Okay, and its algebraic part is non-empty only if it is a translate of a subgroup. And then the idea is that, okay, suppose that we have a torsion point of order H here. Then by Galois theory, you have a lot of points, torsion points on this set. From the other side, if we look on the, okay, so we have number of rational points is either like this or 0. Okay, but by Wilkie it is, okay, it is grows sub-polynomially. So it means that for big H you cannot have torsion points, because if you have one, you'll get immediately a lot of them, which is forbidden by Wilkie. Okay, so okay, so in other words, bottom line is you use Wilkie to show that the number of points is small, and then you use Galois theory to show that their number is big or 0. Together, it means that their number is 0. Okay. 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 So, what can be improved? So the
how the Galois conjugates are? How do we guarantee that they are skewing the Galois?
no. V is defined. Yeah. It's yeah. Okay. Так. No, okay. So how we can improve this thing? We can improve the. Okay. So we have this constant here. So if you improve this constant, then okay, we get kind of this bound becomes. If you know both B and C, then this is an effective bound. Okay, so it makes sense to try to improve this, to find this C effectively. Okay, and the better bounds. If you assume more about set A, then you can hope for better bounds. So the Gall proved in 2017 that you can compute constant C for semi-Noetherian sets, which kind of which remains a word. So there are like Pfaffian functions. There is the Pfaffian functions are defined by triangular structure on the Pfaffian forms. So if you take out this triangularity, you get Noetherian functions, and which are still good. Okay. Okay. So what I'll speak about is that there is a. If you assume more on A, you get better bounds. so, okay, so the Wilkie conjecture, it was in the same article where they proved with Pila, the Pila-Wilkie theorem. They formulate the conjecture that if your set A is definable in Rx, so it is definable in the O-minimal structure, which is called Rx, then, in fact, the growth is not sub-polynomial, but polylogarithmic. Okay, so Rx means that, okay, you take all equalities and inequalities. Everything happens on the real. So you take equalities, inequalities, intersections, projections, whatever you want. You get some set. And these are sets which are definable in Rx. So the general, so conjectures, okay, is still open. Okay, what we did, we considered the similar structure, restrict elementary, RE. Okay, so what is the difference? Okay, the instead of following EX, the whole function on the whole line, it just cut it on the interval 0, 1. Just take this function defined on the interval 0, 1 and extend by 0. And okay, we add to polynomials this function and sign defined on interval 0, pi. And these are the sets which we obtain. So we take equations, equalities, inequalities with these functions, build sets, take their projections, union, intersections, products. We get the O-minimal structure, which is called RRE. Yeah.
Both O-minimal, so RE and Rx are both O-minimal?
Yes, they are both O-minimal. So for RE, it is sub structure of analytics, sub-analytic structure. But for Rx, it was the famous result of Wilkie, which he proved that this is O-minimal structure.
Not a complete, and then randomly somebody goes O-minimal.
No, okay. All this band. Okay. Details. Okay. So what we proved that this for sets definable here, the polylog bound holds. So there exists some degree and the least constant such that, okay, we have this. Okay. So why? Okay. So why RR is good? So it was essentially used. Okay. So there is a kind of the reason is that we can make the effective computation of this structure. In this structure, we have natural notion of complexity of the set. So you kind of can, by how complicated formula, how much is complicated is the formula defining the set, and because of the phenomenal theory of Khovansky, we can effectively bound the number of zeros of these functions from this structure and so on. So this is, in some sense, they are as convenient as polynomials. So as for polynomials, we have Bézout theorem that the number of zeros is the product of degrees. Here we have similar kind of in spirit bound provided by phenomenal theory of Khovansky. So here is the kind of the crucial. So I'll try to, okay, so the ideology here is that real numbers are much better than the complex numbers. And the kind of why it is so, because we have Descartes rule. So if we look on the polynomial in one variable and look on the number of positive roots, then the number of positive roots is bounded not by the degree of the polynomial, but just by the number of monomials in the polynomial, or number of sign changes, no, but not the degree. And you prove it with Rolle theorem, kind of the high school proof. And the Rolle theorem exists over R and doesn't exist over C. This is the reason why R is better. And so the Khovansky idea was that, in fact, what is kind of, Rolle-Khovansky lemma extends this type of arguments to all dimensions, to singularities, kind of. He built a whole theory about this, and the ideology there is that the complexity of the function is not the degree of the polynomial, but degree of the Pfaffian form which defines this function. And from this point of view, all monomials are have the same complexity because they are defined by this form. All monomials are defined by this form. By this Pfaffian form, and the difference is just the coefficient. It is not the degree of the form. So so from this point of view, all these functions are the same, and you get kind of universal bound for complexity of real sets defined by these functions. And this is something which is absent on the complex, because, for example, if you consider, I don't know, e to the x minus 1, it has just infinitely many zeros, kind of in complex domain. So phenomenals are better. So so how we prove how Pila will prove their theorem. So now I'm trying to explain how the proof works. So the idea is generalization of the Bombieri-Pila theorem. You have your set A. Before it was just a curve gamma. And as we cover the curve gamma by images of the interval, we'll cover the set A by images of squares, of cubes of the same dimension. And now we construct the same interpolation determinant and make the same computation. What we'll get is that from our set A, we'll find the polynomials if on our set A sufficiently big. If you take a small piece of this set, then all this piece, the rational points are intersection of this set A with some polynomial of degree d. So what we'll get is that the points we have to count lie, in fact, on a finitely number of intersections of our set A with polynomials. And then we should continue by induction, because for curves we kind of already know how to do it. So so this is A, and this is S alpha. Yeah. Okay. So turns out that unexpectedly the hard step is going from back in the induction procedure. So by one step of this interpolation determinant, we decrease the dimension. But now we have to do all this again. And we have to cover the intersections by images of cubes of one dimension less. And the problem is that this is unexpectedly hard question. And so what Pila and Wilkie noticed that one can, if you look on this proof with interpolation determinant, we didn't use that the functions are analytic. We just use that there is a CR smoothness. We use Taylor series with remainder up to order R. So it is enough to take just smooth parameterization instead of analytic, where R is sufficiently big, depends on epsilon. And it turns out that one can construct CR parameterizations of the sets which appear here, this all kinds of curves. inside the set A, we can, there is a uniform bound on the number of cubes which are needed to cover them. But, okay, and this is generalization of Yomdin-Gromov theorem. And the bound grows to infinity as R goes to infinity, and there is a good hyperbolic reason for impossibility to build this analytic parameterization. So there is this, we have CR parameterization here. So we are always analytic, even sometimes algebraic, and suddenly we jump to CR parameterization. Turns out there is a good reason for all this stuff, which I have no time to discuss. So the problem is that this CR parameterization. So what we thought about is that, okay, let's go back to complex settings, and then let us try to cover, instead of parameterizing, let's try to cover the intersections by polydisks. So what we do here is something which is motivated by Weierstrass preparation theorem. So we have we defined Weierstrass polydisks. So if we have a purely m-dimensional analytic subset in Cn, we say that product of two polydisks is a Weierstrass polydisk for X if dimension of the base delta Z is M, and the set doesn't intersect the top and the bottom of the of the polydisk. So here it is kind of, it is three-dimensional artifact, so I call it top and the bottom. But the idea is that if you take the, it's like in the Weierstrass preparation theorem, if you have delta Z, over each point you have the fiber, delta W, and you want that the points of your set, that they will not escape suddenly through the boundary of this fiber, but will remain on the kind of in the fiber, and then, okay, get away from the polydisk only from the sides. So we want that, okay, it never crosses the boundary of the fiber. Okay. Then, okay, certainly in this case the number of points is the same. They do not escape anyway. So this is the projection to delta Z, is just a finite ramified map. Denote its degree by E, okay, E of X delta. Okay. Okay. So so it turns out that, okay, so what we want is, so we have this set A. We want to interpolate functions on this set by polynomial in, so from a function f, we want to replace it by some polynomial p, okay, which is, okay, polynomial in z, in W, yeah? Yeah. Okay. So we want to, Holomorphic. Coefficients holomorphic in Z. What? Oh, okay. Oh. So now the okay, the idea is that if you, so we replace f on the set A on the set X by a polynomial. So this operator turns to be bounded if what you started with was holomorphic on the bigger set, on the bigger polydisk. So if you have something on a bigger polydisk and on a smaller polydisk, interpolation is a very good operator. And the, okay, for example, interpolation is given by this integral operator, which is kind of, okay, immediately see this bound from here. Okay, now, so why this is good? Because the main problem with the Gromov-Yomdin kind of, the main counterexample, hard example for Gromov-Yomdin theorem is the family of hyperbolas. So something like this. Okay, so it turns out that the parameterization of hyperbolas is extremely difficult. But from the point of view of Weierstrass polynomials, this is Weierstrass polydisk. It is the same nice good family. So if you have a kind of, this is how the interpolation works here. Yeah, so if you have a, okay, holomorphic function z and w, we can replace each w square by this formula by z square minus epsilon. And from this, okay, the composition, we get our polynomial. It will be linear in w. Coefficients will be holomorphic in z on the base. So in this case, interpolation is, you see, okay. And it turns out that this decomposition is as good as Taylor approximation for Bombieri-Pila type estimate. So before we approximated functions with Taylor polynomial. Now we, and what essentially was important is the number of different monomials of different degrees. And here, okay, the same procedure works as before. So essentially what before was kind of, okay. Okay. Okay, now, so how all this works together? So, okay. So there is some general blah, blah, blah from model theory. So we take O minimal set A. We build a complexification of set using, okay, result of Van den Dries. And the equations will be Pfaffian, so will be covered by Chovansky theory of polynomials with some degree beta. Okay, now we consider covering of X by Weierstrass polydisks. And in each polydisk, we construct algebraic hypersurface exactly as in Bombieri-Pila proof. And we get intersection like before, like this, which I raised. And we continue by induction on each intersection. And everything remains polynomial in beta and log h. So the crucial thing is to construct is this step. So you have a set defined by Pfaffian functions of some degree beta, and you want to cover it by polynomial, by Weierstrass polydisks. And you want to count it by not too many Weierstrass polydisks. So good. So how we do it? So no, okay. So we somehow should use the fact that the set is Pfaffian. So we know how to compute its complexity, its topological complexity, all this stuff. So so here's the example how our proof works for algebraic curve of degree d in C2. So what we so the general general proof is very similar. So we take algebraic curve of degree d, and we want to find the Weierstrass polydisk at the origin, centered at the origin, of sufficiently big size. Okay. The idea is that so we want to find, so we have C2, we have a curve inside. Okay, and we want to find the two orthogonal disks such that if you multiply one by a boundary of another, so we get this okay, three-dimensional thing. So it should not intersect the curve x, yeah, gamma. Okay. So we want to find kind of the condition for the product of 2B disk to be Weierstrass is that gamma doesn't intersect this part. So then, okay, if you take, so let's take any ball which is far from the origin. Okay, if we multiply it just by S1, so on C2 we have action of C star, so okay, of S1, so X, Y, E, I, phi. Okay. So then, okay. So then this kind of rotation of this disk, of this ball, will contain the set which we want to be disjoint from our gamma. So what we want is this ball such that its orbit under S1 is disjoint from gamma. So, but we can do in the opposite. We can fix the ball and rotate the gamma. And so what we get is this set, rotation of our curve gamma, three-dimensional set. So we want to find a sufficiently big ball which is disjoint from this thing. Okay, now, okay, so, okay, the answer is given by Vitushkin formula. So, okay. So again, I go to, so this is, okay, we go to, we forget about complex structure, it's just a set in R arbor, which is Pfeiffian, which is good set. We want to find a big ball outside of this set. So how to do it in R2, yeah? So what is, okay, so we have square 0, 1. Oh, okay, essentially, okay. Essentially, there is a picture. Okay, so, okay, so here how it works for a curve of degree d. So we divide square into this grid, and we want to find the square which is free from this, yeah? So the number of connected component is at most d square. Number of intersections between the curve and the line is in the grid is at most d by Bezout theorem. So it means that gamma means, okay, at most these guys, so there could be components which are, okay, inside. And some components which do not lie entirely in the small squares. So, so this is the total bound on the number of small squares, cells, which gamma can meet. So if we take n sufficiently big, so then we can find a cell which does not meet the curve. So the kind of, okay, the number of connected components is constant, doesn't depend on n. Number of intersections with the grid grows linearly, but the number of cells grows like a square. So at some moment, the number of squares of cells will be bigger than this. Okay. Okay, so this is algebraic case. So for if our set is not algebraic, this Pfaffian, so we need, kind of, instead of Bezout, we need Funomials estimates, but all the rest goes as here, and so we get sufficiently big ball outside. We get Weierstrass polydisk and consider things done. Okay, so I'll stop here.